So in your book, that is Theorem 4.53. Again, we have V always for us is a vector space, and S in V a subset. Then part A is if S is linearly independent, then V, another vector in V, and V is not in the span of S, so not. So the span is a subset and you have something sticking out, so it's not part of the subset. Then you can take S and add V, so the new subset S plus something which is not in the span is again linearly independent. I hope that makes sense. So you add another direction which was not part of S. And part B, again, is kind of the other direction. If you have a set that is linearly dependent, then you can delete one vector and the span doesn't change. So here now, S linearly dependent, then V in S, that means some of the vectors in S can be actually combined as with the help of the remaining vectors. So V in S such that V is a linear combination of the remaining vectors in S and then it turns out if you remove V, you don't change the span. You can take it out because the other vectors are good enough to make it. So then turns out span of V is the same as the span of V, but small v removed. So this means removed. No? And again, showing this is not complicated. I just like to skip it in a sense that I hope it is intuitively kind of clear. If you have an additional vector which doesn't contribute to the span, then you can take it out. And here, if you have something which is not in your span, you can take it in and you can keep the linear independence. So I hope at least that kind of makes sense. As I said, the proof would be also not too difficult. You can always just do it by contradiction, for example. And now, based on this, one can show the following. Theorem 4.54. So essentially, this is only there to prove this and also to help prove the next result. So V, a vector space, dimension of V equal to n. And so it means there is a basis with n elements and S in V a subset. Then we have the following. We have the following equivalent statement. Part A is S is a basis. Then this automatically means S is spans V. And this also automatically means S is linearly dependent. Okay, and also I have to say S is a subset and S has, sorry, I forgot, has n elements. Okay, so, and what you see here is now if it's a basis, it automatically spans. But it turns out if it spans and it has n elements, it's also linearly independent, independent. And why is this? If it's not linearly independent, then you can actually remove an element which has a smaller set with only n minus elements, which will also span V. But that's impossible because we know if you have a dimension V, we really need n elements to span. So this implies this with the help of this result and the fact that we need n elements to span the space. That was our first result. Same thing here. If it S is linearly independent, it has to be a basis. Why is this? If it's not a basis, it doesn't span. But then according to this, we can add one more vector and have n plus 1 vectors which are linear independent. And again, that's impossible according to our theorem 4.52. So again, like I said, for the rest of the section, I will not go into these proofs, but they are always combinations of the things we have seen before. Also, we no longer have to go to coordinates. Also, you can just put things together which we have shown. And this is very nice in the sense, for example, in R3, so the dimension would be 3. If you have 3 vectors which are linear independent, they're automatically a basis. Because remember, A implies B, B implies C, C implies A. So these are equivalent, no? So they all imply each other. So if a vector space has dimension 7, you have 7 independent vectors, that's automatically a basis. If a vector space has dimension 7 and you have 7 vectors which span your vector space, automatically a basis. The linear independence automatically follows, no? So if you put more information in that you know the dimension, then you can also make easier arguments. So that's what this result shows you. Then similar in spirit to this one here is the next result. Theorem 4.55. And I just give you some examples, very basic examples. So V, a vector space, and the dimension of V should be not infinity. Also, it's finite, like 500 or 5 or 2, but not infinity. Also, we don't have too many vectors in there. And S, a subset of V. So now this thing is, if the span of S is V, so the S vectors make up every vector in V by linear combinations, but S is not a basis. So now we have basis and span. So if it's span, it's not a basis, it means automatically they are linearly dependent vectors. And what it means now is if we have too many linearly dependent vectors to span it, we can cut them out and it still make it into a basis. No? Then S can be reduced to a basis. And what reduced means, I make an example in a moment. Also you really can cut out vectors and the remaining vectors are a basis. Part B is if S again is linearly independent, but span of S is not equal to V, so it doesn't generate the whole space, then you can add some vectors and make it into bases. And instead of adding vectors, I see it can be extended. So this is a reduction. The other one is an extension. Yeah. So this can be extended. This one, if it's too large to start with, you can reduce it. If it's too small, you can extend it. And I just like to give an example for this, very basic in 2 dimensions, what this actually means.